Paul, what do you do on a day-to-day basis?
So I actually work in the life science side of the business rather than the CAD engineering side. But the kind of underlying principles are the same in that the goal is to use software simulation and modeling to replicate the real world so that you can do things faster and more iteratively without both the time impact of having to build things or make drugs in the case of the sort of work that my software is used for, to get research and development done quicker. But you also massively reduce the environmental impact because you're not, in the case of chemistry, you're not pouring chemicals down the drain from all the failed experiments because you're doing as much of that experimentation in software simulation before you go to the lab.
How long typically, I mean, this is a sort of an open-ended question, but how long do you spend in the simulation stage before you get to the actual physical, let's try it out?
So that's really kind of what our customers do. And I don't actually have kind of knowledge of the kind of timescales that they're working on. A lot of it is, if you think about the traditional sort of life cycle of a drug design, you start with some idea of what you're trying to target. It might be a protein interaction. Let me give you an example of anti-cancer drugs. Essentially, a lot of chemotherapy treatment is done by trying to kill cancer cells without killing healthy cells. And people are familiar with the kind of side effects of chemotherapy, people's loss of hair and things, because it's a fairly kind of toxic therapy. It's not a sort of medicine that you would be wanting to give a healthy patient to make them feel a bit better. It's about life saving. But if you can get that toxin to where it's kind of needed without it impacting healthy tissue, then you have a much more effective therapy. You can target the cancer with higher doses of the toxin without causing as much damage to the healthy cells of the patient. So one technique that's kind of in research now is attaching the toxin to an antibody. And that kind of essentially detoxifies it whilst it's attached. So it acts like a transport mechanism. But that antibody is key to the DNA of a specific cell type. So the antibody seeks out and finds the cancer cell and only deploys the toxin at that target.
It's amazing, really, isn't it? It's
and these are the sorts of kind of modern medicines that are being designed and developed.
Yeah.
And it's I've personally worked in kind of substance classification for actually kind of tracking kind of what are these drugs, because for regulatory purposes, a drug has to be classified clearly as kind of what's in the pill, if you like. And that used to be really simple when it was a molecule. It was aspirin, or it was the kind of ingredients would be a paracetamol molecule and some caffeine. But when it starts to become an antibody attached, what we call an antibody drug conjugate, then it's a much more complicated picture.
Yeah.
And so classifying those substances becomes really, really complex.
Yeah.
Now, probably more akin to the robotic side of things, I work alongside our material science team, and they are doing modeling and simulation at the chemistry level. So, for example, take a product like a smartphone. The things that have made smartphones more useful and desirable products are they've become lighter, smaller, longer battery life. Now, that battery design is driven by understanding the chemistry in the batteries and trying to kind of improve how that works, more storage in a smaller space. And we have software that can simulate the electron flow in the lithium substrate of a battery. And you can explore how changes in the chemical structure of that battery would impact on either the amount of charge density that could be stored or the ease with which the charge can move across the electrodes, or the degradation problems of the kind of lithium getting bound up permanently, which means your batteries over time fade in capacity.
Yeah. Okay.
And then if you think about the kind of size of your phones, the kind of glass on the front, you want it to be light, you want it to be thin, but you don't want it to smash or scratch easily. So our software is being used to model the chemistry of glass. And the glass that you get on modern smartphones has been designed through software simulation to find doping that can go into the glass chemical composition that improves those properties so that you get lighter, more scratch resistant, and less likely to break, these kind of super glasses that are now used.
We've got a couple of questions about the Living Heart project. Do you know much about that?
I know a little about it. I've demonstrated it as an education STEM tool. I was hoping to bring it to PyWars last year before the conference had to be postponed.
Somebody is asking, how do you get access to the project?
So at the moment, the only kind of times it's out on the road is when we're either doing a school STEM event or it is taken along to kind of trade conferences that the company runs.
Right.
All of the information about the project itself is on the 3ds.com website.
Okay.
But to actually get hands-on with the kind of simulation, that's something which is I think we've in this country we've only got one of the simulation tablets that lets you kind of interact with it in 3D.
Yeah. One question from Mark Mellors. This will have to be the last one. I've heard a lot about how design software automating design tasks will change the role of engineers and possibly reduce jobs. For example, automatic gearbox design based on initial requirements. I assume the job losses is just fear-mongering and the work will still be needed, just in a slightly different way. Do you know when automated design tools may start becoming more available?
So I don't know anything about the time scale for that kind of thing because it's not the part of the business that I work in. I mean, automation in design is something which is growing all the time. In the Dassault video, there was a section on clash avoidance in the CAD design of a car, and that's in the software today.
Yeah.
So it actually rearranged the parts, redesigned the parts to kind of make the ducting not clash with the body of the car, just by kind of clicking on it and doing a clash reduction algorithm.
Cool.
So there is stuff in there. The other aspect you may have seen is what you call generative design. So examples of this might be you've got a need for a certain amount of strength against the forces needed in, say, a motorcycle wheel, because it's spinning at extremely high speed. So you don't want it to break apart under that rotational force. And the traditional engineering approach would be you'd build a motorcycle wheel and you'd spin it on a test rig and see whether it broke.
Yeah.
And you want to make it as light as possible because you want it can spin faster if it's lighter, and then your bike uses less fuel, your bike's less heavy, it accelerates better, etc. So how much metal can you shave off before your wheel becomes dangerously weak? And you can imagine trying to do that in a kind of practical experimental way is expensive and time consuming and potentially dangerous as well.
Yeah.
But if you can simulate those forces, which modern CAD software can do, then you can change your design in CAD and predict where the weak points are going to be. So you don't just get to find out will it break, but you get to see where is it likely to break. And generative design is where the actual shape is kind of they almost look organic. They kind of like sort of grow tendrils through the kind of space to generate a 3D mesh of metal that would be as strong for the weight as possible.
Yeah. All right, cool.
Now, you've got a big problem when you make something like that in CAD, because that doesn't necessarily mean it's easy to manufacture. Yeah, if you imagine something that looks like a sponge, you can't just kind of stick that as a block of metal on a milling machine and get it to kind of mill it out, because the tools just can't get into all the spaces. But 3D printing, additive manufacturing is a massive growth area here. And actually making metal parts. Now, some of the things like jet turbine fan blades are made by 3D printing rather than by 3D printing metal. So there's a couple of techniques. One of them is metal powder, where you fire lasers into the powder and it kind of fuses the metal in the powder into solid metal, and then you take that part out and you kind of anneal it in an oven, and it stabilizes the crystal structure.
Yeah.
So there's huge developments going on, but yeah, quite when it's coming to commercial fruition is something which I don't have that information.
Okay. Well, thank you very much for answering those questions. Thank you very much. And it's great to hear about Dassault, because, as I say, they've been really generous with their sponsorship, and it's just amazing to hear what they do and how they do it.
You're very welcome.